Okay, so talking through practice exam 1, we're looking at aspirin or acetyl salicylic acid. And the remember is we're going to look at hybridization. So it says a molecule, put a triangle around S hybridization. So remember, that's going to be all of our hydrogens. A diamond around SP. Well, we don't actually have any diamonds in this molecule because we don't have any SP hybridized bonds. A square around sp2. So that's any of our carbonyl, carbon or oxygens, as well as the aromatic ring. And then a circle around sp3. That's going to be any carbon with 4 bonds, or an oxygen with 2 bonds and 2 lone pairs. And so it says redraw and label the functional group. So there's a carboxylic acid, there's an ester, and an arene. Then we're going to calculate the ratio of ionized and unionized. So remember, we're using Henderson-Hasselbalch. That's this expression, pH is equal to pKa plus log of the ratio, the concentration A minus, the conjugate base, over the concentration HA, the stronger acid. And so we're just going to plug in. So we have a pH of 1 and a pKa of 3.5. We're going to rearrange algebraically so that we're solving for a negative 2.5, and that's going to be equal to the log of the ratio. If we want to get rid of the log, we end up having to take the anti-log, or 10 to the power. So 10 to the power of negative 2.5 gets us 0.00316. And then if we do that for the intestines, that's the anti-log of 2.5, or 316. So if I think about these two numbers in terms of ratios, if I wanted to convert this into a fraction, if I did 316 divided by 1,000, right, that's how I would get this decimal. So essentially that means that for every 316 conjugate bases, or A minus, I have 1,000 acids, or HA. And I'm going to do the same thing for the intestines, except now, because this is a whole number, it's 316. That means that I have 316 ionized compared to 1 unionized. So in the stomach, I have more HA. In the intestines, I have more A minus. And because unionized molecules, or HA, are lipophilic, that means their absorption will occur more in the stomach because it's the unionized molecule that can cross the cellular membrane. So a good way to think about that is at pH 1, most of our drug is unionized, so it can be absorbed in the stomach. Once it's in the intestine, it becomes ionized, and now it can no longer be absorbed. If we look at problem 2, so how do we calculate formal charge? Well, remember, that's the number of valence electrons minus the number of free electrons plus the number of bonded electrons divided by 2, or you can think of it in terms of the number of bonds. So we're going to draw our Lewis structures, and then we're going to calculate the number of valence electrons. So it's pretty easy to do that. If we just think about the number of valence electrons for each of these, that's our total number of valence electrons. And then we can look at our formal charge. Notice these two, right, have the same type of formal charge, but this is the better structure because that negative charge is on the most electronegative atom. This structure is the least desirable Lewis structure because it has a lot of formal charge. And note that formal charge is on the oxygen, which is positive, right? We don't really want a positive charge on our most electronegative atom. Now, if we think about drawing resonance structures, remember you're moving arrows. And so your preferred resonance structure, right? This preferred Lewis structure. Again, it's this reasoning where you want the charge on the most electronegative atom. Our hybrid structure is going to look something like this. So we know that urea, right, or carbamide, is close to neutral. It's going to be slightly basic if it decomposes. And if we think about, right, from a reference standpoint, how that's going to react, right, here's our urea, right, and I have 2 different ways that I could draw that molecule. And of course, right, I don't necessarily know how to draw this structure, but I could imagine if I think about the addition of a lone pair to something that is electronegative, then I could probably see that. And so maybe the better way to think about it is any one of these mechanisms would work. So I draw my urea and the way that it would interact, right? So any one of these would be acceptable too, right? So hydrocyanic acid, right? I can draw a couple of different ways, but really I'm just thinking about, right, how does this molecule interact with this molecule if I'm given a pKa? So I know that this is a base, I'm told that this is an acid, how do I expect them to behave? And really, at the end of the day, this is a molecule that's going to decompose to form hydrocyanic acid, right, and ammonia. All right, so drawing functional groups, that's something that you can check off of the lecture. If you're thinking about drawing equilibrium reactions, you have the lone pair of electrons on your base that's going to abstract the proton, and you're going to kick the electrons back onto your chloride. That's going to generate a conjugate acid and a conjugate base. If we wanted to create then hydrangeas that were blue, right, we would need strongly acidic soil or pH that's below 6. If we wanted to create hydrangeas that were pink or red, we would need more basic soil, so that's a pH that's above 7. And so if we wanted purple flowers, then those would be neutral soil. And so this is true for certain types of plants like Hydrangea macrophyllae. All right, what about naming and identifying structures? So this is a great opportunity to practice your IUPAC naming system. So remember, if you need to, you can always number your longest linear structure. Remember that each substituent should get a number, and that your naming should always be alphabetical with respect to the prefix, so in this case, methyl or ethyl. If we think about drawing the following compounds, the easiest way is to start by drawing the longest chain, so in this case, pent. 1, 2, 3, 4, 5. I find the 3 position, that's my methyl. I find the 2 position, that's my double bond. Note, this is an example of a molecule that can't exist. Why? Well, because if you think about the structure, it's going to violate the octet rule. So, right, better way would be to actually draw a structure that looks like this. And then 3-ethyl, 3-methyl, 1-cyclohexene. Right, so draw my cyclo, add the hexene at the 1 position. 1, 2, 3 is where I should actually see these substituents. So I would move these over just 1, because right now they're at the 4 position. Sorry about that. It's an example of 2 different versions of an exam. Here, you're going to label the pairs of molecules. So we have stereoisomers, we have constitutional isomers, and then we have different molecules. How do I tell? Well, stereoisomers are simply different in space. Constitutional is a different arrangement. Different molecules are actually going to have different numbers of atoms. Equilibrium. So at pH 5, what is the concentration of hydronium? So I take the negative log of my hydronium concentration. Right, it's going to be pH 5 or 10 to the negative 5, so 1 times 10 to the negative 5th molar. If the concentration of hydroxide is 1 times 10 to the negative 2, what's the pH? So I calculate my POH, and again, that's the negative log, right, of this concentration. That's going to give me 2. And so pH plus POH is going to be 14, so 14 minus 2 will give me a pH of 12. If I think about, right, being able to draw and label acid base, conjugate base, that's identifying my pKa, so that's using this table, right, to be able to predict what direction. So in this case, it's going to prefer HF as the stronger acid because H2CO3 has a higher pKa. In this instance, right, the preferred direction is also left because NH4 plus has a lower pKa than HCN. Here it's going to prefer to go to the right because my acetic acid is going to have a lower pKa than my phenol. And here H3O plus is going to have a lower pKa than NH4 plus, so it prefers to the left. So first reaction is to the left, second reaction is slightly to the left, third reaction is to the right, fourth reaction is to the left. Number 6, this is the relationship between structure and function. So you're just drawing geometry. So bent, 2 lone pairs, 2 bonds. Pyramidal, a linear structure where I have 2 bonds and no lone pairs on the central atom. And then PCl5 is going to be trigonal bipyramidal. If I want to think about why water is polar, but CF4 is non-polar, remember that CF4 is tetrahedral. There are no lone pairs and the vector sum cancels the bond dipoles. whereas H2O is bent because there are two lone pairs and the vector sum of the bond dipoles does not cancel. You're going to use the formula AXE to be able to evaluate water and CF4. This shows you two lone pairs, whereas it's 4 bonds here. Here is one lone pair versus no lone pairs. And here, right, it's no lone pairs versus one lone pair. 3 models we've used so far. Some examples would be Lewis structure or bond dipoles or the atom model. And then what are the benefits? Well, it's going to show Lewis structures are going to show lone pairs and bonds, but not necessarily 3 dimensions or relative size of atoms. And then some other examples would be combustion, 3D structure of molecules, size of atoms, starting materials, products, mole ratios, irreversible reaction, conservation of matter. These are all different types of ideas of the way that you could answer this question. Okay, and I know that there was also a desire to hear about practice exam 2. And so here you're actually doing something very similar. So this is, you're drawing Lewis structure and then calculating the net charge. If you're not sure how to do that, you can always calculate the formal charge for each individual atom. So here there's no net charge. Here there's a net charge of -1. Here there's a net charge of -2. Here there's a net charge of -3. So this would be your most acidic. This would be your most basic of these molecules. Similar to practice exam 1, you're going to have to do something with Henderson-Hasselbalch in terms of calculating mole ratio or pH or pKa. And so in this case, you're thinking about a buffer. And so in buffers, we want a pH that's close to our pKa. So in this case, we choose the pKa of 7.21. And then we're solving for our mole ratio or our ratio of concentrations in this case. And so we're able to get 0.616. Remember, if I wanted to convert that to a fraction, I could just do 616 over 1,000. In this case, my conjugate base is HPO42 minus. My acid, or HA, is H2PO4 minus. If we think about acidic versus alkaline soil versus neutral soil, so in acidic soil, we would have H3PO4. In neutral soil, we would see HPO4, H2PO4, and then in basic soil, we would see both of these. If we're thinking about drawing bond dipoles, the first thing we'd have to do is draw our Lewis structure. And then remember that the bond dipole always points towards the more electronegative atom. And so in that case, we would know that the hydrogen would attach to any one of the oxygens. And you could draw resonance structures to show why you could move that negative charge around to your oxygens. If you draw your resonance structures, one of the things that you're going to recognize is you could take the average of all of those, and that would be your hybrid structure. This hybrid structure simply shows that at any given point in time, my electrons will be along this path between the oxygens. So HNO3 is a strong acid, so I'm showing the dissociation into H plus and NO3 minus. Notice it's complete dissociation. There's also water molecules that are around, and I can show that the conventional way that we've drawn this reaction too. If I think about functional groups containing oxygen, so here are some examples. Alcohol, ether, aldehyde, ketone, ester, and acid chloride, and anhydride. For something like this, I'm really just thinking about the ones that are only containing oxygen, but you could also include an amide or an isocyanate as well, but this would be sufficient for answering this question. Equilibrium reaction, remember there's 2 pKa's. The most acidic proton is the proton on the carboxylic acid of glycine. So the base, sodium hydroxide, is going to abstract that proton, and kick the electrons onto the oxygen. That gives it a negative charge. But sodium hydroxide can also deprotonate the ammonium group, in which case you would generate this structure and water as well. Isoleucine and leucine are constitutional isomers. They have a different number of atoms, but the same number and same type of atom. In terms of naming and identifying structures, so here's an example of 4. So the ethyl pentane, the 5-ethyl, ooh, sorry about that. So this should be butyl, right? No, it's not, sorry. Oh, tired. This is a great example of how it's easy to get off track. Make sure that you're counting the longest chain. right? So this is the longest chain. So at the 5 position, it is an ethyl, right, as a substituent, and that's E, so it comes in the alphabet before M for methyl, and then the 2,2-dimethyl. So 5-ethyl, 2,2-dimethyl-nonane. For C, if you take a look at this, 1, 2, 3, 4, 5, 6 is the longest chain, so that's the hexane. And then this is an isopropyl. This last one can look a little tricky, but remember, you have to figure out what the longest possible chain is. So the longest chain in this instance is a pentane, and then each of carbon 2 and carbon 3 have substituents where it's 2,2-methyl and then 3,3-methyl, so total of 2,2,3,3 tetramethyl pentane. In terms of drawing the structures, again, remember, start at the end, draw the longest linear chain, and then you can go back through and fill in. So in this case, 2-ethyl, 3-methyl, and the double bond. 1,1-dimethyl cyclopentane. So it's a cycloalkane and then the 2 methyls. And then in this case, it's heptene, and you're going to draw in your 4-methyl, your 3-propyl, oops, sorry, that should have one more bond there. And then your double bond. So this is an example of, right, make sure that you are fully drawing in your substituent. So this should be 1, 2, and then there should be one more bond here for 3. And then draw as many possible constitutional isomers for hexanol as you can. Make sure that you're not drawing identical structures. Here are just some examples of what you can do. This problem is very similar to what we saw in practice exam 1. So POH and pH, you can calculate at 14. Remember, that's at standard temperature and pressure, so it's neutral. You calculate the concentration, it's going to be acidic. And then if you think about the products for the following reaction, again, you're going to go through and identify. So 12.67 is the pKa for this molecule, 9 is the pKa for HCN, 7.21 is the pKa here. So it's clear that this is the stronger acid and stronger base, and these are going to be the conjugate acid, conjugate base. And then direction of equilibrium is going to be to the left, where H2PO4 is a stronger base than HCN or HPO42-. Structure and function, so tetrahedral, tetrahedral, bent, and linear. Remember, you'll have access to your ideal and molecular geometry worksheet, so you can do that analysis. Why phenol is polar and benzene is not. So here you have a net bond dipole. Here you have no net bond dipole. And then bond angles are different. This is all about lone pairs. So the presence of lone pairs has an impact. Here I have a lone pair, here I have a lone pair, here I have no lone pair. And that's going to make the angles change due to electron repulsion. And the last one is the total number of valence electrons is the first step you should always do for a Lewis structure. Then you're going to complete your octets through bonds and lone pairs. You're going to determine formal charge. And then you want to make sure to check your structure. If you're not sure, remember the equation for formal charge is the number of valence electrons minus the number of free electrons plus the number of bonded electrons. And remember, you're doing the number of free electrons and the number of bonded electrons in a parentheses. I'll make sure to write that in and repost the key. Your three-dimensional structure tells you the occupation of space. The bond dipoles tells you something about reactivity. And then compare and contrast the models. How are they similar? How are they different? Just words versus ball and stick, which is 3D. They're the same type of atom and number of bonds. Although your Lewis structures have lone pairs and bonds, they also tell you about the types of atoms and the number of bonds. Hope this was helpful. We'll talk with you soon. Thanks again.